All right, so now we're going to take a look at how we classify matter in a slightly different way, according to the arrangement of the particles in a sample. And when we go through this classification, what we're going to encounter are three physical states of matter that we see a lot of. And that includes solid state, like a solid state, which we abbreviate as just a lowercase s, liquids, lowercase l, and then we have gases with a lowercase d. We're going to take a look at some of the differences between these three classifications of matter and what makes them different, obviously, but then some other characteristics as well. So in a solid state, in the solid state, what we're going to see is that the particles are arranged. First of all, the particles are fixed, meaning they don't move. The particles are also very close to each other. And typically what we also see is that the particles are arranged in a very ordered fashion, meaning it's like a uh, repeatable arrangement, I think, for example. Okay, so if I were to draw, if I were to zoom in on a sample of a solid, you get the particles here. The word particles could mean an atom, or it can be a molecule, for example. Doesn't really matter. The particles, the building block of the solid, they're packed very close together. So we're super close together, like this. You can't pack them any closer together than they are in a solid. And it's a repeating pattern as well, which is we often refer to that repeating pattern as sort of like a lattice arrangement. So they're really close together. They really can't move. They can maybe vibrate a little bit, but that's as far as they can do in terms of freedom of motion. And what this means then, so in terms of some of the characteristics of a solid, is as follows. So a solid has a definite or a fixed shape. It doesn't change. Solids also have a definite or fixed volume as well. So the amount of space that it occupies is unchanging. Well, right, so that's a solid. In terms of a liquid, we're going to see slight to moderate differences here. So in a liquid, what we're going to see is that the particles, again, they can be atoms, they can be molecules, whatever. The particles are close together, but they can slide past each other. Okay, so that's a lot more freedom of motion that they have than what they have in a solid. The particles are close together, but not as close together as in a solid. Those are two main differences. The where you find them, they're not really an ordered arrangement. Obviously, they're able to slide past each other, so there's sort of a lattice type arrangement. So if I have a sample of a liquid here, and let's say this forms the surface of the liquid, I have a liquid particle here, another one there. So you can see they're a little bit more spread out. They're still kind of close to each other, but not nearly as close together as they are in the solid state. And then I'll draw a little arrow here that shows that the particles can kind of slide past each other as well. Okay, so if you were to zoom in on a sample of a liquid, you would see something like this happening. Okay, so what this means in terms of shapes and volumes, right, is that a liquid does have a definite volume, a fixed volume, but the shape is not fixed. So the shape of the liquid will actually depend on the container. Okay, and it's going to fill or take the shape of the container to the extent that it fills it. So as an example, if you have let's just say a bottle of water. Let's say this a bottle of water like this. And I put some water in here. And let's say there's 50 milliliters of that H2O. Now, obviously, if I take it and pour it into a different container, like doing like this, I may see that the shape that the water adopts now depends on the container that it's in. I'm going to pour all of it out. It's still going to be 50 milliliters, but the shape then adapts to the shape of the container, right? And that's because the molecules or the particles are able to slide past each other. All right, and then that brings us to the last physical state, and that is the gases. Yeah, I mean, the gas, the particles are sort of on the extreme, so they're definitely not close together. They are more spread out. The particles spread out very far. Relative to the sizes of the particles themselves. And the other important difference with the gases is that the particles are in constant random motion. So they're zipping around randomly. They're running into each other. They're running into the walls of the container, for example, and they're bouncing off. So there's constant motion involved with gas particles. Now, if I have a model here, with a gas, this is a gas particle, maybe another one, and another one, and another one, and another one. So they're spread out, okay, and they're zooming around with a great deal of speed. Eventually, they're going to run into each other. They may run into the walls of this container, and then they're going to have all sorts of characteristics and properties associated with them, which we'll talk about in a lot more detail later on when we get to the chassis section. So in terms of volumes and shapes, so the volume of a gas depends on the container. And what we find is that the gas will expand, fill the entire volume of whatever container that it's in. The gas expands, fill the entire volume of the container, and that has implications for the shape that the gas sample adapts or adopts as well. The shape that you use shape of the container also. If you have a sample of gas in a gas cylinder, well, the shape that the gas sample adopts is the shape of the cylinder. If you allow the gas to escape into a room, well, then the gas particles expand out, separate from each other, and they adopt the shape of that room as well. Okay, so there's some big differences between solid state, liquid state, gas state. Sometimes you'll see the word phase kind of being used interchangeably. They don't technically mean the same thing, but for our class, we can use them interchangeably. All right, so we have our solid, liquid, and gas. If at any point you get confused about some of the characteristics of the solids, liquids, and gases, you can always think about the one substance that actually does exist under normal everyday conditions in all three physical states, and that substance is water. Okay, water has a chemical formula H2O, which we probably seen before. So water exists in all three physical states. So solid water is called ice. Liquid, you just call it regular water, and then water in the gas phase, we call water vapor. Okay, and that's because the term gas can also be known, also known as vapor. The gas state or the vapor phase, gas phase, the vapor state is also used interchangeably, right? So we've dealt with, we've worked with, we've used all three physical states of water, some of us every single day. So we know some of the characteristics of these. Now, when we go from one physical state to the next, what we're going to encounter are changes. I can spell that changes in state, or changes in phase. So as we talk about these, we need to know the terms, the terminology, and then also a big part of chemistry and science and physical science also is exploring not just matter, but also when matter changes from one form to another, the energy associated with those changes. Okay, so we'll look at the energy changes as well. So let's take a look at a few of these changes in physical. The first is going from a solid into a liquid. Okay, and again, if you ever get confused about these, think about the one substance that does exist in these physical states. You think about solid water, so ice going from solid to a liquid. Obviously, we made that process that is called melting, or the technical name for it is fusion. Okay, and as you know, in order for ice to melt, we need to provide heat. Okay, so heat is needed. And that process of requiring heat is called an endothermic process. Okay, so right there, two terms here on the left that we'll see. So endothermic, endo means to the inside, thermic meaning heat. So heat required. And then the opposite of that would be a process where heat is released. You probably guess what it is. That's exothermic. And you're obviously in your profession, fire profession, the fire service, you encounter exothermic processes all the time. Fire is an exothermic process, right? Produces a bunch of heat energy, light energy, etc. So we'll try to color code these as we go through. So solid turning into a liquid, that's melting or fusion. That's an endothermic process, heat is needed. Going in the opposite direction, we'll do that in blue. We're going from a liquid back into a solid. That is known as freezing. Think about putting some ice in, I'm sorry, some water in an ice tray, stick it in the freezer. It's a freezing process. And obviously now, in order for the liquid particles to slow down to turn into a solid, you have to take energy away, take heat energy away. So energy then is released. That's an exothermic process. Right? So we're at the liquid phase. How does the liquid now turn into the gas or the vapor? I'll hit both of those things here. Gas or vapor phase. Right, so think about liquid water turning into water vapor. What do you need to do to make that happen? Well, you need to provide heat as well, right? So heat is needed for that process, whatever that process is, we'll see in a second. So heat needed, heat required. So that means it's endothermic. Okay, and think about how you turn liquid water into the gas phase. You usually provide, stick it in a pot, stick it on a stove, and you give it a bunch of heat energy, right? So that obviously is called boiling. The technical name for that is vaporization. turning the liquid into the vapor phase or the vapor state. All right. So we're going in the opposite direction now, going from a gas back into a liquid. That process is called condensation. Okay, and as you can imagine, heat energy is released in this process. And that would make it then exothermic. Okay, so if you think about if you get a burn, right, getting burned with hot water obviously is very painful. But getting burned with steam is a little bit more painful because what happens is the steam, the water vapor, when it hits your skin, it condenses, releases a bunch of energy to your skin. So you get burned by that process. And then you get burned by the hot water that results from that as well, right? So a steam burn can be very, very, very painful, as some of you may have experienced. All right, so we've seen how we can go from the solid to the liquid to the gas or the vapor. Can we go from the solid to the vapor and skip the liquid phase altogether? The answer is yes. We can go from the solid directly into the gas or the vapor phase, and that process is called sublimation. And as you can imagine, heat energy is needed. Thermal energy is needed. So that makes it endothermic. And going in the opposite direction, but before we go into the opposite, thinking of sublimation processes are a little bit more difficult to think of, but one thing that you may have used before that sublimes at normal room temperature is dry ice. So dry ice is nothing more than carbon dioxide. But it's carbon dioxide in the solid phase. And in the normal condition, it goes from the solid into the gas phase, right? And that's called sublimation. It skips the liquid phase altogether, hence the term dry ice. Going in the opposite direction, and if the conditions are such, we can skip the liquid phase altogether, going in the opposite direction from a gas into a solid or vapor into a solid. That's called deposition. And as you can imagine, heat energy is also released in this process. So it is an episode. Okay, so you'll see, different variations of a diagram like this if you look on the online resources, but the idea is the same, right? So you have the three physical states that we can connect via these phase or changes in physical state. We need to know the terms associated with them, but also the energy changes associated with them as well.